Faulkner, and I'm the Executive Director of the Southeast Cement Promotion Association. On behalf of all the conference sponsoring organizations listed in the program, we'd like to welcome you to our 20th Annual Virginia Concrete Conference and our first ever virtual conference. We continue to get high marks for the technical nature of this conference, and that is due to the hard work of the Planning Committee and the excellent speakers we have been able to draw. We have certificates of attendance prepared for the attendees whom requested them on their registration forms. Mary Lynn will be emailing those out next week. I'm also pleased to report that this year we have set an all-time conference record for registrations at 680. And I'm looking now at YouTube, and it appears at this point we have 241 people joined us on YouTube. Conference materials are available on our website, www.secement.org, under the events drop-down menu, including a list of attendees. We count on feedback from you about the conference. Mary Lynn will be emailing you a link to the online evaluation form after the conference is over. Your evaluation feedback will help us plan for 2022. Last year's exhibitors and sponsors were listed in this year's program. As a big thank you for being loyal supporters of this conference. Please take a moment to review that list, and we're looking forward to them all returning next year for our 2022 conference. We are going to be giving out two $100 gift cards, one at the end of presentations today and one before we adjourn on Friday. Winners will be announced each day and contacted following the conclusion of the conference tomorrow. As most know, this conference has had an M&M contest tradition, but it's kind of hard to eat M&Ms virtually, so there's no contest this year, but be ready to eat plenty of M&Ms and submit good guesses next year. The agenda and speakers for this conference were put together by our planning committee listed in the program. This group has done an amazing job of putting together another quality conference. A few housekeeping details. You'll receive an email later this month indicating when the presentations are posted on the VDOT Materials Division website. As the presentations are playing, speakers will respond to your questions as you submit them in the YouTube chat feature. If you want to submit a comment or question, you will first need to be logged into your Google account. Please submit as many questions as you like. And as a final thank you, please join me in giving a big thank you to Mary Lynn Stovall for all of her hard work in making this conference happen. She spent countless hours preparing and organizing all the materials for the conference and handling registrations. Also, a big shout out and thank you to Cade Cooper and Justin Floyd of VDOT for handling our YouTube broadcast today. And thank you to Marie Derby with Argo Cement as our planning committee chair. With that, let's start off today by hearing from Chief Deputy Commissioner Rob Carey, Commissioner Stephen Britch, and Secretary of Transportation Shannon Valentine. Thank you.
Hi, I'm Rob Carey, VDOT's Chief Deputy Commissioner, and I'm very happy to join you today. I've been with VDOT since 1992 and was appointed by Governor Northam in 2018. I certainly have seen the value of partnerships like this that VDOT enjoys with industry, the Concrete Association being no better example. Without you, we could not achieve all the great things that are being done for the residents of Virginia. I'm very happy to be joined by two of Virginia's best transportation leaders who I'm very pleased were able to join us today. With me today are Commissioner Steve Britch and Secretary Shannon Valentine. Commissioner Britch was appointed as the Commissioner of Highways in January of 2018 and brings extensive transportation experience to VDOT. He is also a non-voting member of Virginia's Commonwealth Transportation Board. Prior to his appointment, Commissioner Britch served as a Vice President with Kimley Horn Association and led Kimley Horn's efforts across their 3 Virginia offices. Before joining Kimley Horn, Commissioner Britch served in several senior roles with VDOT, including Research Scientist, Assistant State Traffic Engineer, and Design for Design Safety, and Director of Operations. Commissioner Britch holds a bachelor's degree in Civil Engineering from ODU, and a master's in civil engineering from the University of Virginia. He's also a licensed professional engineer in Virginia and Maryland. Secretary Valentine was appointed Secretary of Transportation by Governor Ralph Northam in January of 2018 and oversees Virginia's multimodal transportation system, crossing 7 agencies with over 10,000 employees. As Secretary, she also serves as Chair of the Commonwealth Transportation Board. Secretary Valentine is a former member of the Virginia House of Delegates as well, which serves her very well in her role in understanding in intricate detail how the General Assembly works. Following an assignment as the Director of the Transportation Policy Council in 2013 for Governor-elect Terry McAuliffe's transition team, Secretary Valentine was appointed as the Lynchburg District Representative to the Commonwealth Transportation Board in May of 2014. And during this time, she created the first regional connectivity study in Virginia that correlated transportation decisions with workforce, transportation, and business expansion, recruitment, investment, covering 8 modes of transportation. Secretary Valentine was named the 2017 Transportation Woman of the Year by WTS, Women in Transportation Symposium, Central Virginia chapter. She has also been honored with the Humanitarian Award by the Virginia Center for Inclusive Communities, Democracy in Action Award by the League of Women Voters, Freedom Fighter Award by the NAACP, Woman of the Year in Government by the YWCA, and Commonwealth Autism Services Award. She graduated Phi Beta Kappa from the University of Virginia in economics. She graduated from the Sorensen Institute at UVA and completed Education and Ministry, a 4-year theology course through Sewanee University School of Theology. So we're very excited to be here and thought we would try something new this year with this approach. Obviously, it's a new format, and as many things we've done over the year have been. So let's touch briefly on the past year. What are some of the key takeaways from 2020, Secretary Valentine?
Oh my goodness, what a tough way to start the conference with such a powerful question, because thank you, Chief Deputy Commissioner Rob Carey, for those introductions. That was a lovely introduction, by the way. You know, it is impossible to be at a meeting, and I can say this with the Commissioner as well, to be at a meeting these days and not recognize the time in which we are living. I believe all 3 of us would very much like to be at your conference, and I say hello to you, Mr. Faulkner, for having us, and I thank all of you who have really made concrete a foundation for our business a priority. Throughout this pandemic, from the very beginning, I will tell you that our priority has been the health and safety of our employees, our partners, and our customers. That has remained consistent. And throughout this, the entire Secretariat, from the Port of Virginia, aviation, trucking, rail, barges, the entire Secretariat, there has been a commitment to transport critical goods and to connect people to essential work, food, medicine, and now vaccines. And for those of you who are here today, I do want you to know that our moderator, Rob Carey, has been playing a very instrumental role. He not only takes special assignments on, such as this one, he's actually been on special assignment with our Secretariat of Health and Human Resources. And he and Heidi Underwood have been leading a team in Virginia to set up a statewide network and to roll this vaccine out as effectively and efficiently as we can. And so I know, Commissioner, we both really want to thank you, Rob. Is there anything transportation can't do?
Absolutely not.
Commissioner, is there anything you'd like to add?
There are a couple of takeaways that I have from 2020. And Secretary, I think you hit on a couple of them. The safety side of our employees and the resiliency of our workforce. Those are, I think, probably 2 of the most important items today that we can reflect on a full year later since the pandemic started. But I have to commend not only our VDOT workforce, but also our partners who have continued to be able to deliver the projects and our services back to the citizens of the Commonwealth, all during the pandemic, with not even once lifting our foot off the gas pedal to be able to deliver them. And that's tremendous. You know, the teams have remained flexible. We've had to learn how to work in the new normal, as we like to say, safely, all while we're resilient in figuring out how to deliver those projects and those services being safe. To me, our workforce has kept one thing in their eyesight, and that's delivery of the projects on time and on budget. So kudos to our staff, kudos to our team, kudos to the people that have been out in the workforce day in and day out since last March with never questioning anything, and then those that have been fortunate enough to be able to work from home and continue to meet our on time and on budget performance for those projects. Thank you.
And Secretary Valentine, the commissioner talked about keeping projects on time and on budget. What about the money side of this? I mean, that clearly has played a role during the pandemic.
Well, yes, they've all gone hand in hand. When we got the initial forecast back in August, we were looking at about an $870 million reduction in transportation revenues through FY22. So certainly managing that, and now even with updated numbers, the early years may not be quite as difficult, but it appears that the recovery may take longer. So we are trying to integrate all of this into our system. And as the commissioner, talked about our workforce, and I believe we have the best in the world here in Virginia. I will say that what makes it possible is the leadership from both of you as well. So I really thank you for helping us. We went to the governor and the General Assembly during the special session in 2020 to seek a budget amendment giving the Commonwealth Transportation Board flexibility just for 2 years, but would allow us to redirect resources so that we put every dollar to work in our 6-year improvement plan. By looking at those funds that we have on projects that do not need those funds until perhaps years 3, 4, 5, and 6, but allocated the funds in the early years, by using those funds today, we have managed to keep every project in the pipeline on time according to their own schedules, not have any delays, cancellations, or reductions in workforce. I believe that this comprehensive look has been a way for transportation to contribute to the recovery and the sustainability of Virginia's economy.
Absolutely. Now let's turn a little deeper on the issue on everybody's mind, which is transportation funding. Secretary Valentine, the governor's omnibus transportation bill made a lot of changes in how we fund transportation projects across the Commonwealth. Could you speak to the reasons for the bill and what it accomplishes?
Well, some of you here today may remember that we passed the Interstate I-81 interstate bill, which was a big surprise for us in 2019. We managed to get that through, and it was such a success that the following year we ended up getting 21 studies, one of which was a sustainability study looking at revenues for transportation over the longer term. What is the impact of electric vehicle penetration, the impact of fuel efficiency? And through this year-long sustainability study, working with an incredibly diverse group from the petroleum industry to the environmental community, we developed the omnibus transportation bill that was introduced by Speaker Phil O'Corn and Senator Saslaw. In that bill, it truly does transform how we structure transportation funding. We tied it to a rising index, the Consumer Price Index. We created a governance structure for transforming rail in Virginia, and we created the Commonwealth Transportation Fund. And through that, we have made a commitment to a multimodal system. The good news is we use concrete across all modes of transportation, as it turns out, so it's important all the way across. But that bill was instrumental in helping us manage the uncertainty and the reductions we are facing through the pandemic. While through FY27, we were hoping for about $500 million of new funds per year, we're now looking at $200 million. It's certainly much less than what we thought, but we in Virginia are managing this unprecedented time I think in a very proactive and responsible way.
Absolutely. Thank you, Secretary. Commissioner, what impact do you think that the omnibus bill will have on future projects across the Commonwealth?
So, Rob, the Secretary once again it started off the conversation to say that even with the planned reduction from COVID being around $800 million a year, the omnibus bill is expected to, as she just said, generate significant funding for future projects in moving forward in the outer years. $500 million when it's fully funded, if we can recover sooner from the COVID, but dedicated $200 million in the outer years. With the omnibus bill and the approved flexibility that we've been able to achieve for the CTB funding that we achieved out of the special session, we don't foresee any project delays or cancellations. And I'll say that, as we've said in the past, 2020 has been a year that we've solely focused on making sure that we did not impact any project or delay any project. So those two accomplishments in themselves, I think, are success coming into the 2020 or 2021. In fact, these actions by the General Assembly, not only from the flexibility that have been achieved in August of this year, but also the omnibus bill, they create the sustainable project pipeline that VDOT has talked about since 2018 that's in our business plan. And that normalizes our traffic or our projects that we can expect to see in the out years rather than peaks and valleys. We're going to normalize this, and we have the sustainability back in our program. And when we create sustainability, then we can advance our major initiatives that we've seen. Look at Interstate 81 and the success that we've had there. The Hampton Roads Express Lane project, and looking at the budget that was passed this weekend, has provision in it to be able to finish off the remaining piece of that if the traffic and revenue forecast comes back in a different way. Looking at the potential for the I-64 gap between Richmond and Williamsburg to be able to close that initiative, all the way to the I-495 project next. So having these projects and having the funds being indexed, as the Secretary said, to Consumer Price Index, creates that sustainability in the funding stream, creates sustainability in our project pipeline, and really helps out. My opinion is the contracting industry and our consultant industry to be able to make Virginia a vibrant and healthy place to work.
Absolutely, and I will certainly say from my perspective that the fact that we have 3 regional transportation authorities now in Hampton Roads, Northern Virginia, and the newest one in Richmond, the funding from the omnibus bill, really in my almost 30 years at VDOT, I don't think I've ever seen a time where I felt better about the future and the funding and the programs that we have in place, particularly with Smart Scale, than choosing those projects that get done. I just think it's a very, very bright future for VDOT across the state. So with that, I'd like to, if you all, and I'll start with you, Commissioner, any final thoughts you'd like to share?
I think I do have a couple of final thoughts, Rob. First, I'll say I'm happy 2020 is over and we can see a light at the end of the tunnel. So I'd like to be able to have this meeting and all future meetings in person. I think we're heading in there. As the Secretary said in her opening comments, with your role over with Secretary of Health and Human Services, I appreciate what you do on a day-to-day basis, and then taking that role on and advancing the opportunity to continue to have a major impact back on the citizens of Virginia. So thank you for that. So I do have some additional final thoughts for you. That we know change is constant, and even it's accelerating. And we know that we're going to need to continue to invest in our most valuable resource, and that's our people. So for VDOT, that means keeping our focus on the VDOT of tomorrow and readying our staff for what lies ahead, both tomorrow and decades out. So investing in our people has to be a continuing theme. And stepping out of 2020, we never thought that we would see telework to the extent that we have. We've been fairly successful. We are going to start talking about some reconstitution plans this upcoming week with our workforce, but we will forever have changed our workforce, and the need for that change is just going to continue to see a trend that our people come first, and we're going to have to make sure that they're ready for it. The second thing is that we need to continue to examine our regions and our corridors that have the most significant transportation issues. And why I say that is that because we're going to have to address them in a very systematic manner. And so how can we achieve that? I think we can achieve it through a couple means. One is to continue to focus on our performance-based planning process and our performance-based management process. We're going to also need to continue to focus our energy on creating that project pipeline initiative. We've had some initial conversations with the Commonwealth Transportation Board. I would envision that we continue to have this, but this will continue to set the sustainable pipeline of projects and know well in advance of where those projects are, the impact that those projects will have, and the return on their investment. And then finally, look to fund all those initiatives, I think, through the operations, the Interstate Operations and Enhancement Program. And I think this is a key, is that through that program in itself, we've started having that dialogue on ensuring that operations remains a core function of the agency, has a focus on the agency, and it's just not about expanding capacity. It is really utilizing the existing capacity that's in front of us today. With this work, we're going to be able to continue to build Virginia's world-class multimodal transportation system.
Absolutely. And Secretary Valentine, you know, from your position, you obviously oversee all of transportation in Virginia. And, you know, what are your sort of closing thoughts on where we are and where we're going?
You know, it's hard really to add to what the commissioner said, because, you know, everything that you just mentioned really is the foundation for going forward. Our people, the leadership, and I think our determination to solve problems in a very smart and targeted way. I think we are very deliberate in that process, and I believe that, Rob, that's a great deal of why we are in the position we are today. I will say, the enthusiasm with which the commissioner said he's happy 2020 is over. I think we are going to learn a lot of lessons from 2020, and it's going to be easier, Rob, when we all have vaccines, admittedly. But looking back on this past year, I think one of the lessons is going to be the vital role transportation plays in our lives with real people every single day, in economic growth, in helping us be connected, in helping Virginia to be competitive, and in creating an economy that works for all people. I believe that is fundamental to who we are, and this pandemic has shown us some light that can help guide us in being just more attuned and more effective going forward. So I believe that we're going to learn a lot from this past year and build on that. And while, you know, we are fortunate to be in this position, we recognize very much the gaps that we have because of how we have managed the pandemic. We're going to continue to work on those issues, work with our federal partners. We were able to get some relief in the most recent COVID relief package. We are targeting those funds and continuing to work in Washington with the new Biden administration, Secretary Buttigieg, and our federal delegation, in making sure, you know, Virginia is on the front lines of what the future of transportation is. And I look forward to doing it with the great leadership we have here at VDOT, with Commissioner Britch and Chief Deputy Commissioner Carey, and with all of our partners here at this conference.
Well, Secretary Valentine and Commissioner Britch, on behalf of everyone joining us today, I want to thank you for taking time out of your busy schedules to share your thoughts with the conference attendees today. Clearly, there are bright days ahead for transportation, and thank you for everything you do every day to keep Virginia's economy moving, the transportation system moving, and making Virginia a great place to live and to raise a family. As I always tell the employees of VDOT that we're not about transportation, we're about quality of life, and I think you've demonstrated that here through your comments today, that it is really about quality of life for all Virginians, and that's what all of the men and women of VDOT are focused on every day, and our partners, like those here in the Concrete Conference, play a big part of that, foundational to everything we do that make life better in Virginia. So again, thank you, Secretary Valentine and Commissioner Britch, for your time today.
Thank you. Have a
Thank
great
you, Rob.
conference.
For everybody listening, please understand we're always so appreciative to hear from the commissioner, the secretary, as well as the deputy commissioner. Their comments put us a little bit behind, but we'll do our best to try to get us back on schedule. With that, I want to go ahead and introduce the first session of today on the VDOT policy updates, recent standards, and revisions. The two speakers are Susan Keene with VDOT Location and Design Division and Bruce Shepard, VDOT Structure and Bridge Division. Susan has a bachelor's degree in engineering science and physics and is a licensed professional engineer with over 25 years of engineering experience in both the private and public sectors. Susan joined VDOT in 2012 as the Richmond District Location and Design Engineer, and in 2014 moved to the central office as an Assistant State Location and Design Engineer. In April 2017, she was promoted to the State Location and Design Engineer. Bruce has a bachelor's degree in civil engineering from Virginia Tech and is a licensed professional engineer with over 30 years of engineering experience, all with the VDOT Structure and Bridge Division. In May 2019, he was promoted to Engineering Services Program Manager, responsible for maintaining the manual of the Structure and Bridge Division.
Good afternoon. My name is Susan Keene, and I serve as VDOT State Location and Design Engineer. I appreciate the opportunity to share some updates from our division this afternoon, but before I jump into those, I kind of want to give you some background on how we arrived where we are today and shed some light on our path forward. My updates primarily revolve around changes to our roadside safety hardware. So I kind of want to walk you through some of the history behind where we have been and where we're headed. So in 1993, NCHRP published Report 350, and it introduced matrices for the testing of roadside safety hardware. Most of us have heard about safety hardware that's NCHRP 350 compliant. That just means that it was designed, tested, and evaluated using these matrices. It provided for test levels 1 through 3 that specified speeds ranging from very low up to 62 miles per hour. These test levels were for passenger cars and pickup trucks only. Test level 4 was for single unit trucks or box trucks. VDOT at that time required that all new roadside safety inventory meet this criteria, and that includes our permanent and temporary concrete barrier. Well, then in 2009, AASHTO's Technical Committee on Roadside Safety, they also update the Roadside Design Guide, published the Manual of Assessing Safety Hardware, or MASH. This committee is made up of volunteers across the state DOTs. They relied on a report or a project from NCHRP 2214, or Improvement of Procedures for the Safety Performance Evaluation of Roadside Features. This report primarily focused on the changes of the vehicle fleet from 1993 to the current day. So if you think back of what vehicle you were driving in 1993 versus what you drive today, for me, I went from a little Honda Prelude to an SUV. It is reflective of the changes to the current fleet and the fact that the percentage of SUVs and quad cab pickup trucks have increased. This manual used the knowledge gained from testing devices over the years and really advanced the science behind the crash testing. It added additional tests in the area, with changes to the impact angles, including the reduction of the oblique end impacts for gating terminal and crash cushions. It was changed from 15 degrees to 5, and that is probably one of the biggest factors and the biggest changes with MASH. The other change was increasing the size and weight of the test vehicles. For example, the light-duty quad cab pickup trucks in MASH are much heavier and higher in center of gravity than the heavy-duty pickup trucks from the NCHRP 350 study. So one of our focus areas for Virginia has been the Virginia Strategic Highway Safety Plan, which is focused on reducing fatalities and serious injuries due to a multitude of issues that we've identified. One of those is roadway departures. So this focus area takes a two-pronged approach in addressing those issues. One, reducing the likelihood of leaving the travel lanes, and if a vehicle does leave the travel lane, then trying to minimize the adverse consequences. This can be done through engineering by improving the ditch and backslope designs, relocating or removing fixed objects, or incorporating roadside safety hardware and devices. With this focus on roadside safety, VDOT's Chief Engineer Garrett Moore in 2009 launched the VDOT Strategic Guardrail Management Program. This management program was in part to upgrade the obsolete roadside safety hardware that we had in our inventory. But the first crucial step in upgrading the hardware was understanding what hardware we had and where it was located. So as part of this program, VDOT established the statewide inventory database, which is an ArcGIS application that contains all the guardrail systems, and it's updated by district staff when a component is damaged or replaced, or if it is upgraded through the Strategic Guardrail Program. As part of this database, we're working to include concrete barriers in the future. In addition to setting up the Guardrail Management Program, VDOT also joined the Midwest Pool Fund at the University of Nebraska in Lincoln. This helped us facilitate our transition to the latest hardware and pool funds with other DOTs in order to access and understand testing results. So as a result, VDOT has changed our standard design to a 31-inch Midwest guardrail system. That is reflected in our current standards. And under the Strategic Guardrail Management Plan, we've replaced or upgraded about 900 obsolete terminals and then installed a total of 100 MASH terminals across all of our programs. This includes new construction, our HITS program, or upgrades under the Strategic Guardrail Replacement Program. This in turn helps us improve safety and minimize the adverse consequences for those roadway departures. Now on to items that are more specific to this audience. In April of last year, VDOT introduced the new standard TBC1, or the Freestanding Temporary Concrete Barrier. As you may have noted already, there is additional reinforcement and changes to the pin and loop connections between the barrier segments. There's also an additional required upstream and downstream anchorages. In addition, there's a requirement for embossing the manufacturing date. And this new design was tested to the MASH test level 3. Now let's take a look at our next item to update, which is the permanent concrete barrier design. Pictured here is the F-shape barrier with a guardrail attachment. You can see the reduced post spacing in the attachments to stiffen the guardrail system and reduce pocketing where those two systems meet. This F-shaped barrier works by lifting the vehicle center of gravity to reduce momentum and redirect errant vehicles. This was tested under test level 3 under NCHRP and may not redirect the larger vehicles due to the height of the barrier, which is only 32 inches. This is due to the overhang of those large vehicles like a single unit truck or box truck. In addition, it has a 3-inch lip at the bottom, which can accommodate an overlay, but the multiple slope shapes must be retained in order for it to work as designed. So this is a picture of a constant slope barrier at Texas A&M Transportation Institute in College Station. California and Texas developed these constant slope barriers to meet MASH and to help redirect those larger vehicles. The testing that they have done has shown that a minimum height is needed to redirect those larger vehicles. The Texas constant slope is similar in performance to the Jersey shape, and the Caltrans is similar in performance to the F-shaped barriers that we have. There again, this taller barrier helps to resolve the issues with the overhang of those box trucks. So as a result, VDOT is moving forward with adopting a 42-inch constant slope barrier. This provides protection for the current fleet, but also gives us the additional capacity for those larger vehicles like the single-unit trucks. Another advantage of the single slope barrier is that it maintains functionality even with multiple overlays, as long as the height remains adequate to redirect those larger vehicles. So in reality, it has the potential to redirect large vehicles such as box trucks or single unit trucks and operate at a test level 4. In general, for high-speed highways, the single slope barrier is most appropriate to limit those rollovers, especially since much of the fleet now has side airbags to help absorb that impact and improve the safety of the occupants. The new concrete barrier standard will replace the F-shaped standards, and the old standards will be sunset at a later date that is yet to be determined. If you have questions or want further information, please feel free to reach out to Chuck Patterson or Matt Cross in our standards division. So our next steps are targeting a publication of this new constant slope barrier for the spring of 2021. We're going to continue to collaborate with Structure and Bridge on the design of the grade differential application that would be similar to our NV8 standard. Another obstacle or hurdle that we need to overcome is the development of new drainage standards that will work with the new constant slope barrier. And we are asking to partner with PCAV to assist us with the development of those new drainage standards. And obviously, we don't quite have a sunset date on the existing standards since we still have quite a bit ahead of us to do. And there's projects that are ongoing with the old standards. So we're going to work to establish a logical sunset date when the new standard is released. With that, those are the updates I wanted to share. I hope you found this presentation informative. We will be available later for questions in the Q&A, and I will have Chuck and Matt with me also. So thank you, and we'll talk to you soon.
Hey everybody, glad to be at the Concrete Conference. This is Bruce Shepard. I'm the Engineering Services Program Manager. I think I'm on take 47 trying to record this. I'm starting to think that it's harder to record than it is to do it live. But nevertheless, we'll give it a go. We're going to talk about updates that happened in the year 2020 to our office practice and standards. Here's an outline of topics we'll cover today. It's a lot of them, but don't worry, we're not going to get into the weeds on all of these. Our goal today is to give you an awareness of the updates that were made. So down the road, you may not remember the specifics, but you'll recall that, hey, an update was made, something about that topic. So, and before we get into the actual updates, I want to talk a little bit about what is the Structure and Bridge Manual. Sometimes I fall into the trap of assuming that everybody knows what it is and where it's located and our terminology. But there's the web address, and here's a screenshot of the website. And you can see that the Structure and Bridge Manual is made up of all the parts shown there. Part 1 is the preface, Part 2 is the design aids, which we also call the office practice. Then parts 3 on are various standards. So Part 2, the office practice, has 33 chapters, so there's a lot in that. Today we're going to talk about updates that were made to Parts 1, 2, 3, and 7. Steel or concrete? As you're working on preliminary plans for new or replacement bridges, one of the key questions is, what kind of superstructure can you use? If conditions allow uncoated weathering steel, the Stage 1 report can compare steel options and concrete options. But if conditions do not allow uncoated weathering steel, approval is needed in order to use steel. So this is a new requirement. It was added in April of 2020 to Chapter 11, the steel chapter. So keep that in mind when you're preparing your report and recommending a superstructure type. Design waivers and design approvals. Who is the approval authority? This is all spelled out in Part 1 of the preface. For design bid build projects, design waivers, some require state bridge engineer approval or disapproval, and others are submitted to the district bridge engineer. The preface outlines which go to which. Design approvals, they generally all go to the district bridge engineers. But new in October of 2020, all items proposed by a concessionaire or design builder must be submitted to the state bridge engineer. So that is a new requirement. Pre-stressed piles for full integral abutments. Typically steel piles are used in full integral abutments. Piles need a little more flexibility in full integral abutments, so that's why the steel piles are normally used. The office practice was silent on the use of pre-stressed piles. It's not that they weren't allowed, it just we were silent on it. So recently we added in several places in Part 2, we added some guidance to help the designers think through, hey, will a pre-stressed pile work in this situation, and what are some things to consider? Special provisions. There was an effort in 2020, and it's still ongoing, to turn some common project-specific special provisions into standard special provisions. So this list of provisions right here, drilled shafts, thermal integrity profiling, MSE walls, and then the three at the bottom which go with voided slab or box beam bridges. They've been around for a while and you guys are probably familiar with them. But up until now, they haven't been published. They're what's considered project-specific special provisions. So we're working with the subject matter experts in construction division to get these published. And once they're published, here's a screenshot of the construction division's website. They'll be right there in that zip file for everyone to access when they need to access them. Take a look at the white blocks in the photo. Those white blocks are elasticized expanded polystyrene, or EPS. And EPS goes behind our back walls, our full integral and semi-integral back walls. So in the photo, the contractor will install it behind that back wall. We've used EPS for 15 to 20 years in the same fashion. Early on, there were several suppliers, but at the moment, there's only one known manufacturer of elasticized expanded polystyrene. There are several that supply and manufacture expanded polystyrene, but we need the elasticized version because it has can compress and rebound. Because there's only one manufacturer that we know of, Construction Division and the FHWA considered a proprietary product. So in 2020, we had to obtain a public interest finding from the FHWA in order to continue using it. So there's your manufacturing opportunity. If someone wants to get into the business of manufacturing this, well, there's very limited competition, and that would be great. High-load multi-rotational bearing standards. One part of the update was the tables. Here's an excerpt from the tables, which shows the loads that need to be given. And so the old table just had a few loads, and the new tables, you can see there's more loads that need to be given. Also updated as part of that were the notes to the designer, and also we added a layout sheet that is required to go with the HLMR standards. Chapter 13, which is a new chapter, was added for some general design information. In April of 2020, we added Chapter 18, Earth Retaining Walls. Right now, the content is mainly focused on MSE walls. It contains the approved retaining wall systems list. This list used to be in Part 11, the geotechnical manual, and Part 11 has been disseminated through various chapters in Part 2. Steel girder standards, which is in Part 7 of the manual. Forgive me, I realize this is the concrete conference, but I do want to make you aware that we updated all of our steel girder standards, and the camber diagrams were a big update. So you can see the old diagram and a new diagram. I just picked a 2-span to illustrate. So a couple differences is you can see the intervals there's more intervals, and also the reference line. The old reference line was a horizontal line. The new reference line is not a horizontal line. And we worked with some fabricators to see what would best meet their needs, and this is what we ended up with. The tooth joint standards were updated. One of the updates was the triangular teeth for curved alignments. We added that. On the left, we have the uniform teeth. Now, we still have that, and that's the preferred option if you can, but in situations where you have curved alignments and the movement is not necessarily parallel to the girders, we have the option for triangular teeth. One thing you want to pay attention to, though, if you are using the triangular teeth, is that AASHTO has some limits on that dimension there circled in red. So if you exceed those limits, you're not allowed to use the triangular tooth. Another reason the tooth joint standards were updated is because of the advent of Virginia abutments and Virginia pier caps. Most tooth joints will be used at either Virginia abutment or Virginia pier cap. And in those situations, the trough membrane is not needed. So here's a visual of what happened to our standards. So before we had 5 tooth joint standards. Now we have 11. And so the yellow is the triangular teeth that we talked about, and the green is the standards that would be used with Virginia abutments or Virginia pier caps. So because of those, the standards went from 5 to 11 that we would use. So debonded strands. So debonded strands are only allowed for the bulb T-beams, the PCB T-beams. And they've been allowed, so that's not new. But we did add recently some material and fabrication info to Chapter 12, the pre-test chapter. And these are some notes, and they're not on the standards yet. So because they're not on the standards, a designer would have to add these notes from Chapter 12 onto the bulb T standard. Well, that's it. Thank you for listening. Enjoy the rest of the conference, and I'll see you down the road.
Bruce and Susan, at this point, would you like to make a few comments or respond to any questions that came up on the chat?
Right now, I'm not seeing any questions in the chat. I know that Chuck and Matt are also online if folks have questions.
Well, hearing none, thank you both, Susan and Bruce, for excellent presentation, and we'll move on. Try to continue to catch up with our schedule. Thank you very much.
Thank you.
Next up on our agenda, all right, you're welcome. Thank you. Is the West Virginia Unbonded Concrete Overlay Project, and the speaker today is David Chulo with Golden Triangle Construction. David works for Golden Triangle Construction. He's been there for 23 years, starting from a field engineer to the vice president of construction. He oversees all field operations in their heavy highway division. He graduated with a Bachelor of Science degree in civil engineering from the University of Pittsburgh and is a licensed professional engineer in Pennsylvania.
Good morning. My name is David Sciullo. I'm with Golden Triangle Construction. And today I'm going to present on West Virginia Route 30 concrete overlay project in Chester, West Virginia. This is not an old technology. They've been doing concrete overlays for a long time. They've done a few in the 1980s in Pennsylvania. They've been doing them all over the country. However, just in the last, say, 10 years or so, it's been really taking off throughout the country. And we were happy to be the low bidder on this project. So location of the project. So here is downtown Pittsburgh. Here's the Pittsburgh Airport. It's about an hour west of Pittsburgh. This is the Pennsylvania line here. You have the Ohio line that runs along the Ohio River. So this is in the furthest north part of West Virginia. So zooming in here on the project itself, the stars represent the limits of the project. So you have main line Route 30 ends right here at the bridge, which eventually goes over the Ohio River. Route 2 limits are here, and on and off ramps all included in the project. The description of the project, it's like I said before, it's the first one ever in West Virginia. $4.3 million contract. The original schedule was April through August. The whole intent was to get the project done prior to school starting in September. We were still able to do that despite the rainy weather in April. We really did get started until May, but we're still able to get the job done before school starts. 20,000 square yards of 7-inch overlay on an inch interlayer, asphalt interlayer. 4 interchanges, and also Route 2 was involved in the project. There was some preservation, patching on Route 2. There was some variable depths, full depth reconstruction at the tie-ins to the bridge and Route 2 and County Road 30, which paralleled project. I'll explain that a little later. Minor median work. There was a concrete channel that was rebuilt, and the median barrier was also reconstructed. There was also an interesting clause in the contract. There was a no excuse incentive decentive clause. So the specifications called for a 9-day closure of Route 30 to complete the overlay work. That included patching, repairs of the roadway. There was small repairs that needed addressed. I'll explain how those were addressed. You had to place the asphalt interlayer. You also had to do the overlay and the shoulders. And that was 4 lanes on 3,600 feet of roadway in 9 days. A tall order to that, for sure. So the way this no incentive decentive clause works is, so if you get it open in 9 days, you get $90,000. If it takes you 10 days, they take $10,000 off that incentive, and you get $80,000. Up to, say, 18 days, you get 0, and so forth. 19, you lose 10, 20, and now you start being assessed liquidated damages for anything beyond that 18 days. So it was a challenge, of course. So we internally, we looked at some things we can do to help the project schedule, change some designs of the project, and approached West Virginia on these changes. The first one was Route 2. Now, if you look at the plan for Route 2, you had all those hatchings would be patches that needed done on Route 2. Again, there's a lot of patches on a small area of Route 2. So we looked at it and seen, well, maybe we could reconstruct the whole thing for the same cost as it was to patch the roadway. I mean, the patches look like checkerboards. We thought we could do it. We priced it up. It was attainable. So we approached West Virginia with it, say, hey, we can give you a new road for the same price, and we're going to construct it the same way. Flagging operations while we're in that lane, it will be done the same way. It's just we're ripping out the whole road and replacing it with a new road, still saving the curb gutters that was planned for the project with some minor patches to those and give them a new road. Again, looking at overview of the road, you have 3 lanes here. You had a parking lane and you had 2 through lanes. So we did them 1 lane at a time. We did the parking lane, maintained traffic on the through lane and the opposite lane. While during work hours, we would flag one of those lanes to pave the curb lane, say. And then we'd move our way across the roadway and just keep shifting traffic as we did the work. Picture of what we did here. So you have, this would be the parking lane. We saved the curbs here. Again, traffic's maintained here while we're working, flagging that lane. Then we'd open this lane up at night when we were done. Again, the curbs were saved. Here's a look at what it looked like when it was done. Again, brand new road for the same price as all those patches. Time-wise, too, it was similar time because the excavation didn't take very long. Looking at the overlay here, this was the proposed section. So you had 7-inch pavement, and looking at that roadway, that's 2 lanes wide. You had asphalt shoulders because we're building everything up 8 inches, so you had to build the shoulders up 8 more inches. And on the existing, that was just overlaid on the existing asphalt shoulders. The overlay was on top of a 9-inch existing concrete pavement. Again, we discussed, how we could maybe look at changing a few things, and this is what we decided on. Since, we have a concrete plant there on site, instead of doing the asphalt shoulders, we changed those to concrete for the same price as the asphalt shoulders. So all we did was added tie bars to the shoulders and extended the asphalt inner layer. That's only probably a couple feet, burned it into nothing. And now you got 8-inch shoulders for the same price as you did 8-inch asphalt. It was a no-brainer for the department. They accepted that without question. Another change we've made, we looked at the detour and the 9-day closure and seen how we could make this better. I mean, it was a 20-mile detour during those 9 days. Not ideal, especially for the locals there in Chester. They weren't real thrilled about that, but they understood, the project needed done. So we looked at, is there another way we can do this? Maybe somehow maintain traffic while we're working. We've done this in the past, doing overlays, maintaining 1 lane each direction. So we come up with a new detour, and kind of combination of a detour and single lane work. So there was a parallel road that ran along Route 2, was County Road 30, and very capable roadway to handle the traffic. So we looked at detouring westbound traffic onto that roadway, construct the eastbound lanes using long-term single lane closures. The ramps were still closed per the contract, except the westbound ramps were closed during the detour. So it eliminated an additional couple ramp closures. I'll show you here in a second. And then also eliminated the incentive-decentive clause. What that did was obviously eliminated some risk on our end, but also saved the department money. Then they didn't have to pay for that $90,000, assuming we got done in 9 days, which we still intended to do. But again, there was still some risk there. Looking at the modified detour, it kind of looks fairly simple. So here's the County Road 30 that paralleled Route 30. The issue here was on this farthest west eastern end, this piece of the job started right here. So to construct this was somewhat difficult. We had to do that in single lane. After the road was done, the detour was over, we opened the road. We did this separately, 1 lane at a time on the weekends, flagging, a little bit difficult, but actually if that only little piece saved the whole entire detour, was worth it. Eastbound, we did 1 lane at a time. Traffic was able to come across the bridge eastbound instead of getting off and heading back here towards that 20-mile detour. The locals were thrilled with it because they didn't have to deal with that detour, 20-mile detour. They were still able to get to where they were going easily with this small little detour. So just to go over the construction, primarily overlay, not to get into anything else. I don't have much time for that, but looking at the overlay itself. So the first thing you had to do was you had to go out and look at the existing pavement, determine areas that needed full depth repairs. Now, normally on a full depth pavement job, you'd look at areas where there was cracks and you're going to do full depth patches on these new roadways or on this preservation job. However, this is a little different. I mean, you'll see cracks on the roadway. However, if the cracks are not moving, in other words, if the slab, has no movement to it, it's still okay for an overlay. However, if the slab has some movement, some faulting, you'd want to replace that slab, patch, or whatever you need to do so you wouldn't have movement. Ideally, you want uniform surface underneath that overlay. So what you do, you go through there, you look at the areas, you proof all the pavement. We did it with a loaded triaxle to see if any areas of that pavement needed fixed with full depth patching. Well, it's very little actually. And also there's areas where you would say you had potholes or small repairs that needed fixed. You'd use like a fine asphalt sand mix or cement grout to fill those depressions so you'd still have a uniform section underneath that inner layer. That's ideally what you're looking for, uniform, because that concrete provides an adequate base provided it's stable. And if it's stable, there's no sense in doing patches if the slab is stable. So looking at some photos here of the existing roadway, this is looking eastbound. So these little areas here is what I'm talking about. If this slab with these cracks in it is not moving under load, there's no reason to remove them. So what you would do is you'd clean these out very good and either use that, like I said, that asphalt sand mix or concrete grout, which we elected to do because we had a batch plant on site. We could batch the grout ourselves. We'd go through there, clean them out, and put grout in there prior to us doing the asphalt interlayer to create that uniform surface. Here's one area where we did some patching. This was a skinny, not even sure when this was done, but we replaced some of this, not a lot of it, some of it. The areas were bad. Just did a full depth repair to create a stable, uniform surface. Some of these areas here, probably cleaned these out if they were loose and put grout in them. Another look here, you have some areas here. Again, you're not touching these cracks, just filling in the holes. I was trying to search for some pictures of that operation and really didn't have any good ones to share with you. Apologize for that grouting operation. So looking at the asphalt, just again, typical 1-inch asphalt placement, no different than regular asphalt. So you place that 1-inch interlayer. Then, on a slip form process, just like regular concrete, you're placing the concrete in front of the paver, placing a 7-inch overlayer. Like I said, we extended this asphalt 1.5 foot or so beyond the limits. Here's another view of it. And here we did stringless paving. You can see the prism here. I'll explain that in detail a little bit later. Get another view of the paving. This would be westbound. Here's the eastbound lanes. You can see the edge of the asphalt on the right side here. This guy here, most important guy right here, is the dump guy. He has to make sure that he doesn't overload the paver. So again, critical to get uniform head in front of the paver to maintain pressure, uniform pressure in the front. That way you have consistent, smooth concrete coming out the back. So he's communicating with the paving operator to make sure, he's not overloading the paver and keeping, you don't want to starve the paver either for concrete, but making sure you have consistent, even head in front of the paver. Here's a look at, after paving, we got some excellent rides on this, 50s, 60s on this overlay, minimal grinding just up at the very ends where we did the tie-ins. We had some grinding on some handwork sections at the very ends of the job. Again, you could see the asphalt interlayer went a little wider here. And the tie bars. So the tie bars, again, are spaced 2 feet apart on a 6-foot joint. So here's these blue marks, if you can see, are the joint marks. And you got 2 bars per bay. So you have 6-foot bay, 2 bars per joint, 2-foot distance in between them to keep away from the transverse joint. Another look at construction. Another look right after paving prior to spray curing. Here's a look at the 4-foot shoulder on the westbound, that'd be the westbound off ramp to Route 2. I talked earlier about the transition to existing. So we had a few areas like that. One especially was down by the bridge. So say this was the tie-in to the bridge near Route 2. So you had the existing 9-inch pavement, 1-inch asphalt interlayer, and 7 inches concrete. So total 17 inches. You had a transition from 17 inches to 9 inches. So this would be the existing subbase here. So what we did was we paved transitionally from 9 inches to 17 inches. So you did have 17 inches of concrete right here at that interface. Well, here's a look at us paving it right on the existing subbase. Just like regular concrete. We dug it out, regraded the subbase, and slip formed the concrete right on top of the subbase. Another view of it coming into the overlay from the bridge. Again, maintaining traffic while we're paving here. As you can see right here, traffic is running right here. Got a little bit too far out, but traffic was running there. This is looking eastbound from the eastbound on-ramp. This is when we were paving the barrier. You can see the median barrier here. Again, this is asphalt underneath the overlay here. I look at a slip form in the barrier. Here's a this is looking eastbound from the westbound side. This is the on-ramp from Route 2 heading west. The bridge is right behind me here. Here's a look heading westbound. Here's the westbound off-ramp. That's the bridge that takes you over to High River. Here's a look at Route 2 intersection here. This is the eastbound on-ramp and the eastbound off-ramp. Again, this is all new construction, so to speak, full depth. I'll explain that here. So the ramps, again, had an area, they weren't very long. So they had, the original design called for a transition here, overlay, and then another transition back down to the bridge. Instead of doing the transitions, we excavated the whole ramp and gave them a new ramp for the same price, because after you do all those transitions, it made more sense just to, instead of doing the overlay, just excavate the whole ramp and replace it in kind right on the existing subbase, and did it for the same price. So they got a whole new ramp for same price as they would get an overlay. A few other items of note. We use an optimized concrete mix. We've done that in Pennsylvania. I've not done it in West Virginia till now. West Virginia was amenable to that change, and it helped us. We thought got a better ride from it with the change in aggregate mix and lower cement contents, and they really get a better ride. Stringless paving was used. It's been around for 10 years now. Those of you not familiar with it, we went out ahead of time and surveyed the existing pavement, created a 3D model, adjusted the profile to make it a smooth profile, because obviously it's an existing roadway, probably a little bit up and down. And I adjusted the profile, minor adjustments to the profile to get a smoother ride. Yes, some of the concrete might have been a little thicker, maybe plus a half inch, not minus, 7.5 to 7. Created a smoother ride than just adding 7 inches of concrete to the existing pavement. We also did non-destructive testing. As you can see here, these discs are placed on the subgrade or asphalt. And after paving, a couple days later, you can use this gizmo here, and that records the depth, sends pulses down to that disc, and gives you accurate depths on the pavement. Eliminates all that Swiss cheese you do to new concrete pavement. Real pet peeve of mine, when you can get accurate depths from this. Very accurate. And that'll conclude my presentation. Again, this is the world's largest teapot. A little history to this. This was located on the infield area right there by the ramp. And it'd be the westbound off ramp right in the infield area. A little history to that is originally constructed as a wooden barrel for Hires root beer. That was the original advertising, supposed to be this barrel for Hires root beer back in the late 30s. It's Latrobe, actually. Someone bought it, brought it to Chester, and used it, made this teapot with it, and was selling antiques and souvenirs out of it in Chester. It changed hands over time. It sat dormant from 1960 to 1980 some, I believe. Then they moved it, it sat dormant, and somebody refurbished it, gave it back to the town of Chester. They moved it to this location, and there's where it sits for the last 20 years or so, or 30 years, something like that. You can look it up online. It's some history to the world's largest teapot. So I will take any questions, and thanks for allowing me to present today. Thank you.
Thank you, David. And if you can unmute and bring up your video. I believe you've got 3 questions on chat on YouTube. If you could see those, can you address those in one by one?
Yes, sure. Thank you, Roger. Appreciate allowing me to speak today. I'll try to address some questions. Andrew, do you have any experience, good or bad, with using geosynthetic layer, interlayer in lieu of asphalt between the new and the old? We have not personally used the geosynthetic layer. We have spoken with some contractors that have used it out in the Midwest, and very successful with it. Much easier to install. It's a lot cheaper. It's been lasting a few years now. There's been some projects. I don't know all the projects, but it's been successful so far. Now, Pennsylvania's looking at an overlay project here in southeast of Pittsburgh, looking at design it with this geosynthetic layer in lieu of the asphalt. So hopefully we can be successful on that project, and we can try it. I'm looking to try that geosynthetic layer. Looks promising. Next question is the asphalt interlayer used as a drainage layer for water to wick through? I don't believe it is. The asphalt layer is almost like a wearing course, 9.5 millimeter. Now I know there's some discussion about water seeping in there and what effect that has on kind of washing out some of that asphalt interlayer, maybe some stripping. So that asphalt has to be You have to have an anti-stripping agent in it, but I'm not aware that's used as a drainage layer. The question, 6x6 panels were used. They were on a 7-inch overlay. And were dowels used for load transfer? They were not. There was no dowels. There was tie bars used on the longitudinal joints, but no dowels on the 7-inch pavement. It was just contraction joints. They were just green cut and sealed, or not sealed. They were just green cut. No sealing on the joints in West Virginia. Another question come up. Was this a design bid build? And is this type of project more ideal for design build? Sounds like numerous changes. I think part of the issue was, to answer the first part, it can be design bid build if it's, I guess, designed properly. And however, the MPT becomes a factor as far as design build. We prefer doing design build MPT projects because we look at, every contractor's a different way of doing things. So based on what their skill set is and what equipment they have. So, we thought it was, better with our skill set to change it up. But I think West Virginia was new to the, as far as doing concrete overlays and actually needed some assistance, and we provided that to them. I think they were very grateful that there was something new they were trying here and making some changes on the fly, getting some help from Concrete Paving Association as well. I think helped the department as well. I think it was a good team effort by both. They were eager to do it. We were welcome to help. I think it was successful. So if there's any other questions, I'd be happy to take them now. Trying to think if I see anything. Hope I answered everybody's question.
Yes, thank you, David. That was very helpful for those. So we very much appreciate you being with us today and answering those questions. Thank you very much.
No problem. Thank you.
We will move on to our next session, which is the value proposition of concrete pipe. The speaker is Trig Huff with the American Concrete Pipe Association. Trig is the Northeast Region Engineer for the American Concrete Pipe Association. He graduated with a bachelor's degree in civil engineering from The Ohio State University. Trig has been promoting resilient infrastructure with the American Concrete Pipe Association since 2012.
Hi, I'm Trig Huff. I'm the Northeast Region Engineer for the American Concrete Pipe Association. In this session, we're going to take a look at the value proposition of reinforced concrete pipe. When exploring the value proposition of a specific product or even an industry, as we're about to do, we need to look at three primary considerations. The first is what the customer or agency needs or cares about. The second is what that individual industry does really well. And the third is what do the alternative product industries do really well. The overlap in the middle of our Venn diagram is the value proposition of that industry or product. We only have 25 minutes together, so I won't waste your time discussing what alternative products do really well. Even those of you not in the pipe industry have heard their claims several times. They're lightweight, they consider themselves sustainable, they have a pretty good joint, and anything concrete pipe can do, they can do better. So let's take a look at just what concrete pipe can do. First of all, concrete pipe is sustainable, but it's not just sustainable, it's also resilient. Secondly, as you all know, reinforced concrete is strong. Third, reinforced concrete pipe provides proven, consistent hydraulic performance. And finally, reinforced concrete pipe has a proven track record. Sustainability can be defined as the ability to exist continuously. While many people primarily associate sustainability with environmental considerations, the core concept of sustainability encompasses much more than that. A commonly used definition of sustainability is meeting our own needs without compromising the ability of future generations to meet needs of their own. If a system is sustainable, it will theoretically remain operational without negative effects to its own functionality or the systems around it throughout the rest of time. Traditionally, it can be compared to a long-term analysis that evaluates the foreseeable future and takes into account our intent for society to be functional for our great-great-great-grandchildren and beyond. That makes sustainability an especially important term and an essential consideration when it comes to infrastructure. Traditionally, sustainability is categorized by societal, environmental, and economic sustainability. These categories encompass what is referred to as the three pillars of sustainability, the triple bottom line, or people, planet, and profit. Infrastructure sustainability must provide dependable functionality while also considering the environmental implications. For infrastructure to be truly sustainable, it must also achieve economic sustainability, meaning it must be economical to construct, but also to maintain. Economic sustainability in infrastructure ensures that as a community grows, it will retain the economic resources necessary to build new systems and maintain and replace existing systems at a manageable rate. Look at this time lapse of the Las Vegas region in Nevada. The community growth is evident both on the street level as well as from the 30,000-foot view. For a given system to be sustainable, designers and decision makers must take life cycle cost into account. Life cycle cost analysis is a methodology that enables engineers, designers, and decision makers to better understand the economic impacts of infrastructure decisions over time. To achieve economic sustainability, engineers and policymakers must account for all economic costs over the lifetime of a project and utilize the right tools and approaches to do so. Unfortunately, according to ASCE, only 59% of government agencies across the U.S. employ some type of life cycle cost analysis to maximize their investments, and even then they rarely extend into storm sewer systems and culverts. If you consider that storm sewers and culverts are still a significant portion of project budgets and designers are presented with many material options for drainage pipes, it is important that life cycle cost analysis be considered for this aspect of infrastructure as well. In order to perform a true life cycle analysis, the designer must consider the initial construction cost, the maintenance costs, and the service life of the product. When we look at the initial construction cost, we consider the installation of materials and the methods used. We should consider the compaction effort necessary to achieve a proper installation for all different types of pipes and culverts. And of course, the cost of pre- and post-installation inspection must be accounted for. When considering maintenance costs, local, real-world experience with pipeline maintenance expenditures may be the best indicator of future maintenance costs for proposed new pipeline project. Proper construction inspection will result in lower maintenance costs over pipeline service life. Without proper inspection, an improperly installed storm sewer or culvert will likely require more maintenance than it would had it been properly installed initially. Agencies should differentiate between estimated future routine maintenance costs and rehabilitation costs. Some pipeline rehabilitation projects, while pricey, may effectively extend the service life of the pipe beyond the original service life estimate. If an agency tracks the actual lifespan of culverts and storm sewers in a local region, a strong case can be made for using that number for service life and life cycle cost calculations. When a storm sewer or culvert is replaced prior to the end of its service life, engineers should evaluate the removed pipe sections for possible reuse in either the replacement pipeline or another pipeline project. Resetting older, undamaged storm sewer and a culvert pipe is a great way to increase the pipe's overall value. This reuse should be considered in life cycle cost equations. Pipe manufacturers' service life claims should be carefully weighed against actual user experience. If possible, you should look for third-party sources that confirm or refute service life claims. The National Cooperative Highway Research Program, the NCHRP, has published the life expectancies for different materials for most conditions. Reinforced concrete pipe has a proven history in many regions across the country, and there are documented cases of concrete pipe that's been removed near their 100-year expected service life in excellent condition. Claims of 100-plus year service lives have been made by manufacturers of other pipe materials whose products have been around for less than half a century and whose performance history indicates something significantly less than 100 years. Flexible pipe products don't share a similar history. Over the years, the plastic and metal pipe industries have introduced new products featuring improved formulations, coatings, and pipe wall section properties. These changes leave designers and specifiers to gamble as to whether or not the new product truly is improved, or just a marketing ploy to assure entities that old-style product issues won't in fact occur with the newer product. Without good construction inspection, an improperly installed storm sewer or culvert can be expected to have short-term or long-term issues that may affect its service life. Relying on life cycle cost calculations to determine which type of pipe material will be used on a pipeline can be problematic if the pipeline doesn't last as long as the assumed service life. The service life of the final installed conduit is the only relevant number. A crushed or squashed storm sewer pipeline could in theory last hundreds of years, but provide little to no water conveyance capabilities. And it's important to remember that a pipe's service life may extend beyond the project design life, especially in the case of concrete pipe. Concrete pipe is durable enough that in many cases at the end of life for one project, it may still be acceptable to remove and reuse that pipe on another project. Because of the present threats that our infrastructure systems face, sustainability should always be coupled with resilience. Infrastructure that is sustainable and not also resilient will inevitably fail because it cannot adequately resist disturbances and will require frequent repairs or replacement. Resilience should thus be seen as a necessary supporting element of sustainability. As the U.S. Resiliency Council said in 2016, many LEED certified buildings in Superstorm Sandy were designed to have a low impact on the environment, but not for the environment to have a low impact on them. And, as Rocky said, it's not about how hard you can hit, it's about how hard you can get hit and keep moving forward. That is resilience. Resilience is an especially important consideration for infrastructure systems because, by definition, infrastructure is the core of how our entire society is able to function safely and effectively. Ensuring resilience is a priority when designing infrastructure helps to ensure that the systems we depend on every day, whether it's buildings, transportation, water supply, drainage, or some other function, will stand strong in the midst of adverse events. Not only does this reduce the inconvenience and safety concerns associated with the loss of critical infrastructure function, but resilience is also a significant long-term cost-saving mechanism. According to a report published by the New World Bank and the Global Facility for Disaster Reduction and Recovery, $1 invested in more resilient infrastructure would result in $4 of long-term benefit over the expected life of the infrastructure. In addition to that, FEMA has found that every dollar spent on disaster mitigation beforehand saves society $6 in the future. Put that another way, infrastructure systems that are not designed with resilience up front will end up paying the price down the line. Let's shift gears a bit and take a close look at the strength that reinforced concrete pipe provides. In order to really understand the strength of a pipeline, you need to also understand the strength provided by the system. In this case, the system we're looking at is the soil pipe system. When we install rigid pipe in a trench, the pipe itself is much stiffer than the surrounding soils will ever be, regardless of the amount of compactive effort placed into the backfill. As this newly installed soil pipe system is loaded, the soils on either side of the pipe will consolidate slightly, and we therefore represent them as springs in this drawing. The concrete pipe itself is so strong that it provides 40 to 80% of the system's strength. As the pipe is loaded from above, the rigid pipe transfers the load through the pipe wall and down to the foundation of the trench. As those soils consolidate over time and through loading, it's interesting to note that rigid pipe actually attracts load due to the friction forces within the soil. So when we design a concrete pipe installation, we must account for the added loads caused by soil consolidation and friction forces. If we do the same exercise with a flexible pipe and soil system, the drawing is reversed. No matter which type of flexible pipe we use, it will always be less stiff than the soils on either side. In fact, in this system, a plastic pipe would only provide between 5 and 10% of the system's strength. In order for the system to achieve full strength, the embedment above the pipe must lock into an arch that helps to distribute the load. As the pipe is loaded, flexible products are designed to deflect and therefore push out on the sides of the trench as well as the foundation. In the flexible pipe soil system, if the soils above work to form that proper soil arch, the flexible pipe is able to actually shed load due to those same soil friction forces that attract load to a rigid pipe. So how do we verify the strength of concrete pipe? If it's attracting extra load, we need to make sure that it is strong. Well, most of you know we use the 3-edge bearing test. So let's take a quick look at that. The 3-edge bearing test is not very originally named. It simply has 3 bearing strips that help to support the pipe and apply the load. This loading situation, without any soil support around the pipe, is the most extreme loading that the pipe will see in its service. As the load is applied by hydraulic cylinders above, the pipe wall is forced into tension and compression. The tension zones are shown here in red, compression are shown in blue. This cutout gives you a closer look at how and why the pipe wall is placed into these zones. If you look at it as a simply supported beam on each end with a centered line load, we can see that the bottom of the beam, or the inside of the top of the pipe in this case, will experience tension, and the top of the beam, or the top of the pipe wall, will experience compression. So just how much strength is built into a typical piece of concrete pipe? Well, let's do a quick calculation. For example, the average white rhino bull weighs approximately 5,000 pounds. A similarly sized 48-inch Class 4 RCP comes in at around 7,000 pounds. The D load, or design load for that class of pipe, is 2,000 pounds per foot of diameter per foot of length. And the ultimate design load for that class of pipe is 3,000 pounds per foot of diameter per foot of length. Now, if we do the math, that means we need to test this piece of pipe to 64,000 pounds service load and 96,000 pounds of ultimate load. Now, that's a lot of weight. In fact, 96,000 pounds is roughly the same weight as if we loaded 19 of those white rhinos on top of that Class 4 concrete pipe. What's interesting, but also kind of intuitive, is that concrete pipe is actually stronger as it gets larger. Here we show the different classes of concrete pipe and the corresponding service and ultimate design loads. Remember, the design loads are based off of pounds applied divided by the foot of diameter and the foot of length. If we look at a 12-inch Class 4 and the corresponding soil load over top of it, and a 48-inch Class 4 with a corresponding soil load above that, remember that's the pipe that can hold 19 rhinos, we see that the 48 is actually 4 times as strong as the 12-inch. And that's actually true right down this entire chart. The 144-inch pipe is 12 times as strong as the 12-inch pipe. That makes sense. The pipe span is larger, so it sees more soil load and loading, and therefore it must be that much stronger. The same cannot be said of alternative products. They actually decrease in stiffness, or at best stay the same as their diameters get larger. That reduction places even more risk on the contractor's shoulders to ensure a proper soil pipe system has been designed and built. Switching gears again, the hydraulic performance of concrete pipe is tried, true, and consistent. One of the perks of using a rigid material is that the roughness coefficient of that material does not change substantially over time. Provided the pipe was properly installed, we can assume that the Manning's N value to be the same number on day 1 as it will be on day 36,500. Again, the same cannot be said for the competition. Plastic pipe has been shown to grow corrugations both in the field and in the laboratory due to its loading. I recently took this photo inside of a Virginia culvert that had been in the ground approximately 10 years. Undoubtedly, the inner smooth wall had very little corrugation growth when it was initially installed. But over time, due to the continued loading of the pipe wall, the smooth inner lining started to grow corrugations that were deeper and deeper, as you can see in these examples across the screen. How does the hydraulic design account for these changes over time? The same question could be asked of metal pipe. While metal pipe does not grow corrugations over time like plastic, it does tend to corrode at a rate that surpasses its design life. Certainly, the flow capacity of this culvert has decreased substantially due to the rust and the lack of an invert. Now let's move on to longevity. It's more than just an industry talking point. As I mentioned earlier, it's also an economical consideration. If we compare two culverts, let's say pipe A and pipe B, you can see how the difference in longevity makes for a much different total life cycle cost. If pipe A costs $1 million to install, but it degrades quicker than its design life of 100 years, it will need to be removed and replaced at a certain value, and that new cost will be another $1 million. Pipe B, on the other hand, has a much longer design life and survives even longer than the 100 years. While the initial cost of pipe B may be 15% higher than pipe A, the fact that it can stay in the ground for 100 plus years makes it a much better choice. No other pipe products are part of the Century Club because no other pipe materials have been in use for 100 years yet. An example of that is this non-reinforced concrete pipe that was installed in Mohawk, New York in 1842 and was still performing its duties when it was retired in 1986. Another soon-to-be member of the Century Club comes from right here in Central Virginia. This cast-in-place box culvert in Albemarle County has been in use under Route 250 for 90 years. And while this pipe is only 70 years old, the agency owner had the contractor carefully remove it so that it could be cleaned and reused again on a nearby project. Now that is longevity. So that completes our discussion on the value proposition of reinforced concrete pipe. We spent quite a bit of time talking about what I think reinforced concrete pipe does really well. We touched a little bit on what alternative products think that they do pretty well. And unfortunately, we didn't really have time to talk about what the customer or the agency wants or needs. And certainly the value proposition is the combination of all three of those in the center of our diagram. So now, in the question and answer session, I'd be interested if you want to add some comments about other items that maybe I missed on what concrete pipe does well, or maybe even some items that alternative products do well. For that matter, if you'd like to add what the customer or the agency needs or wants, that would really add to our discussion. I hope you've enjoyed the discussion on the sustainability, resilience, strength, hydraulics, and longevity of concrete pipe. If you have any questions, I'll take them now, or I'd be happy to discuss later by email or by phone. My contact information is below. Thank you, and have a great rest of your conference.
Thank you, Trig. I'm not seeing any questions on YouTube, but you've got a minute here before we catch up on anything you want to share.
Great. Well, I think we're actually just about back on time with the agenda. So unless there any questions come in, I'm happy to turn my time over to the next presenter if we need to.
Okay, thank you, Trig, and we'll do that. Thank you very much for joining us today, and excellent presentation.
Thanks.
Our next session is the new Frederick Douglass Memorial Bridge in Washington, D.C. The speaker is Ken Butler with AECOM. Ken is the Chief Bridge Engineer for AECOM's North America Complex Bridge Practice. His responsibilities include leading complex bridge projects as either Technical Director, Bridge Lead, or Project Manager, and supporting project execution for all complex bridge projects.
Hello, my name is Ken Butler. I'm the Chief Bridge Engineer for AECOM's Complex Bridge Practice. I'm serving as a design manager on this project we're going to present today, the Frederick Douglass Memorial Bridge Project. It is located in Washington, D.C. It's a $441 million design build project for the District Department of Transportation. South Capitol Bridge Builders is a joint venture with Archer Western and Granite Construction Company, and AECOM, we're their lead designer. So just to get you oriented a little bit, you can see the Potomac River and the Anacostia River. Anacostia River here, Potomac River here, Reagan National Airport, Arlington Memorial Bridge, the Capitol, the United States Capitol, where South Capitol Street comes down and crosses over the Anacostia. And this is where our project is in this vicinity. So the purpose of the project is pretty straightforward. It's to replace a 68-year-old swing span bridge. You can see our new bridge is in red and then the existing swing span here. We are going back with a fixed structure. But it is more than a bridge project. You can see these large traffic ovals on both the east and west side of the river. These traffic ovals are 2 football fields long, a football field wide, so pretty substantial. And then we're also doing reconstruction along South Capitol Street and reconstruction of the I-295 and Suitland Parkway interchange. This is part of an overall expansion of the economic development in this area. This has been a 30-year program, multi-billion-dollar effort. You can see in this upper corner here the clip of the Washington National Stadium, and the new soccer stadium is just outside of the image here. So this project really serves to continue the economic development, with the bridge itself being the marquee centerpiece of the development. So how did we get here? The department really, I would tell you, gave us a blank canvas. They did give us an RFP with technical performance specifications. It was based on a 1,000-point scoring process, 400 points in the technical proposal, 600 points in price. So price was important. Well, what the department did is to ensure that they received the iconic structure that they wanted was they had held 4 or 3 visual quality concept meetings where we had to meet with them, share with them our development, what we were presenting, and they had basically created 15 mandatory aesthetic goals, what they call project design appearance goals. And you had to, these were pass fail, you had to pass these their criteria in order to advance. So I will tell you, from our perspective, it really was a fully integrated effort with our designers, our design team, our contractor and the builders, and our bridge architect, where we got together in long workshops, week-long workshops, and we developed really 30 concepts, from cable-stayed bridges to arches. Ultimately, we really recognized Washington, D.C. as a city of arches. So we focused on that ancient structural form, but we wanted to marry it to modern technology. And what do I mean by that? So a few of the things that we did, some of our guiding principles. we wanted slender. We wanted open. We didn't want heavy arches. We wanted unbraced arches across the top, so parallel arches. We wanted to maximize the height, so we exaggerated the height. In Washington, D.C., there's a guideline. You cannot construct more than 114 feet above street level. So basically, we took 114 feet above the deck level. The 54 feet to deck level is really generated out of the navigational envelope. The nav envelope's 150 feet wide by 42 feet high. So that basically gives you, with the superstructure depth to 54 feet and then 114 above it. So we exaggerated the heights of the arches up to 168 feet. We also wanted to minimize the number of piers in the water. We were allowed by contract 4 piers in the water, minimum spans of 300 feet, but we wanted to stretch these. So we went with two piers in the water, and that's how we came up with this 453, 540, 453 span arrangement. And the other thing, the architect really wanted the arches to touch down on the river. They wanted the feeling of sort of skipping a stone across the river. And then the contractor wanted waterline footings, as you can imagine, to save on cofferdam construction. So we had a sort of a combination of the contractor's viewpoint, the engineer's design viewpoint, and the architect's. Performance specification limited us to the 2 expansion joints, one at begin and end of the bridge. And I'll explain a little bit later on in the presentation why that was important and how we overcame that. From a rest of the presentation standpoint, we're going to work our way from the top to the bottom. So we'll talk about the superstructure and the arch first, and then work down into the concrete V-piers and then into the foundations. The deck itself is pretty wide at 123 feet wide. It supports 6 lanes of traffic and pretty generous pedestrian bicycle paths on either side of the bridge. These are 18-foot wide pedestrian bicycle use paths. The superstructure itself is pretty simple, with steel edge girders, 72-inch deep webs with transverse floor beams. You can see that in the shading of blue. And then on top of that are precast concrete deck panels. And on top of the precast concrete deck panel is a 1-inch PPC overlay, polyester polymer concrete overlay. One of the things we really like about the PPC overlay is that it's placed with a binding course of methyl methacrylate, so that you put this MMA down and it really tends to flood and fill in any concrete cracks or deficiencies, and then the PPC is placed. It's the second time we've used it on a complex cable supported structure. The first time was in the Charles Cullen Bridge in Rehoboth Beach, Delaware. And this project, very aggressive environment right on the Atlantic Ocean. And this overlay has been in place for 8 years and is performing very well. So we have high expectations for the performance on Frederick Douglass. Just to get you oriented here with the framing system, you can see here the concrete V-piers. This is the concrete V-pier here. We have edge girders, longitudinal edge girders, these 72-inch web steel plate girders here. And then we have these transverse floor beams running at 12-foot centers in this direction. And then every other floor beam, so at 24-foot centers, is cable supported, cable stay supported. So the deck panels themselves are right around 11 feet wide by 28 feet long. You can see the gray, basically the gray shading represents the precast deck panels. They're 10 inches thick, and then the yellow, what you see in yellow, are cast in place concrete, the stitching or the closure pours. The belvederes themselves are also, or the overlooks at each V-pier are also cast in place. So a couple things to highlight on the precast concrete deck panels. For Frederick Douglass, again, they're 10-inch deep panels, and we used a combination of stainless steel reinforcement and epoxy coated reinforcement. So the hairpin bars across the longitudinal closure joints are stainless. Everything else, including the hairpin bars across the transverse joints, are epoxy coated. And the joints themselves are 6,500 PSI concrete but the panels are 5,000 PSI concrete, and then again, the 1-inch overlay on top. We went with this combination to ensure a 100-year serviceability life. We'll talk about that a little bit as what we had to look at in that regard. In contrast, we also were designing and building at the same time the Arlington Memorial Bridge right around the corner on the Potomac River for Federal Highway Administration. For this particular project, Federal Highway Administration and their performance specifications actually dictated two things. One, all stainless steel reinforcement, and then two, ultra high performance concrete closure joints. So their UHPC joints, we had a 21,000 PSI concrete first, fiber reinforced versus a 6,500 PSI concrete on Frederick Douglass. And as a result, you can see the closure joints are at 6.5 inches versus our 11 inches and 16 inches. And the only reason why I put this up here is because I think, from my perspective as a designer of record for these bridges, to me, it's going to be a good case study over the years is how they perform. I have high expectations for both. One, Frederick Douglass, combination of stainless and epoxy coated with a really high performance PPC overlay. The other, all stainless UHPC joints, but with a 2-inch latex modified concrete overlay, both constructed at the same time. So I'll look at how these perform over the years. And this view just gives you a really nice view of the steel edge girder and steel transverse floor beam, the framing system with the precast concrete deck panels on top, and then supported by the cable stays. The navy blue paint on the edge girders, structural steel, and then the arches and the concrete V-piers are all painted white, and that was just an aesthetic treatment. Aerial view of the precast concrete deck panel placement. We are placing in progression, so we're working out and building the framing system, grid at section at a time, and then placing the panels, and then you can see the stitching, the cast in place concrete closure pours. You can see the insulating blankets in the lower portion of the picture. So as we move into the steel arches, a couple unique aspects of the arches. Well, one, we didn't go with concrete arches because we were looking at weight restrictions and limitations. These are very deep arches, you'll see in a minute, but very unusual shape, variable depth, kite shaped. We went with internal bolted splice connections. We didn't want anything external for aesthetic reasons, and we wanted an internal connection from the steel arch into the concrete V-pier. So as we look at these, you can see that the view on the upper right, this kite shape that I'm talking about, and at the apex of the arch, top of the arch, it's 6 foot deep. But as it transitions down to the concrete V-pier, it's 14.5 feet deep. So complicated shape as well as variable depth. You can see in the lower right in the fabrication shop, just the depth of it relative to a man. And then in a larger view, you can see just this nice smooth transition here between the concrete and the steel. So how did we accomplish that transition? You see on the left, and what you see highlighted in green, these are 2.5-inch diameter galvanized anchor rods. And they are, the nuts are tightened to 160 kips of tension. And they are cast inside the concrete V-pier, and then they extend into the steel arch. So the gray is what you see is concrete to V-pier, and then up in this blue area is the arch itself. On the image on the right, you can see the internal bolted splice connections inside the steel arch. And then on the left, you can see the last keystone piece of the last arch being placed. This was August of last year. And I can tell you both the fabrication, these were mill-to-bear surfaces, both the fabrication and the erection were just superior. We were within plus or minus 2 inches for every arch as we went to place these last keystone pieces, and they just went in beautifully. So now we're going to talk about the concrete V-piers themselves. And it's interesting how, I told you at the beginning of the slide, one of the things we were limited by the performance specifications was 2 expansion joints, one at basically at each abutment, the beginning and end of the bridge. So we had to accommodate the movement, the thermal expansion and contraction of the bridge through the V-piers. These are not tight arches, they're springing arches. We had to accommodate the full movement. And we had to accommodate that in also consideration of these belvederes, these overlooks. So how did we do that? We basically created these strong backs on the inside face of the arch piers. Bearings are here, and the longitudinal edge girders run in this direction on both sides. And basically the bridge moves like a glide chair in between the V-piers. And we support it to the center of the arch by these outriggers. Basically, the transverse floor beams extend out beyond the edge girders and then provide the anchorage housing for the cable stay and then support it off the arch. So the concrete V-piers themselves, 6,500 PSI concrete, post-tensioned, very large, 113 feet wide by 70 feet tall. You can see the inside strong back in this location, center line of bearings here. And then in this view, you see these 2.5-inch diameter galvanized anchor rods that are cast into the top of the V-pier, and then the post-tensioning anchors in the top. So bring you over here, it anchors in the top, post-tensioning runs down, loops through, and then anchors in the top. Here, it's tied into the footing, you can see in that view. So as we look at the internal post-tensioning, we have a combination of both internal and external. The internal is highlighted in green, the external highlighted in orange. The internal is 8 27-strand tendons, 0.6-inch diameter. They're double-end stressed. We wanted to ensure a good uniform force throughout the V-pier. And then they are housed within grouted corrugated plastic duct. The external post-tensioning is actually used for serviceability. It's only needed when the structure has 8 lanes of live load. It was designed for 8 lanes of live load, even though it's only striped for 6 lanes. But the external PT is more akin to a cable stay. They are 27-strand tendons, but they are co-extruded, individually sheathed strand, wax filled, and then they're housed within an external HDPE duct, which is also wax filled. This just gives you a nice image of the V-pier at around what we call the knuckle. You can see the very complex geometry that you have and the forming that went into this. The contractor never complained about this. They did a great job with it. You can see the rigid galvanized PT duct coming out of the footing and into that lower knuckle. And then all of the epoxy coated reinforcing steel, and then the image on the right, just a side view. You can see all of the duct ports for grouting coming out of post tensioning. Now there are several views, gives you an idea of the robust false work that was required to construct these V-pier legs. In that upper left view, and then in the lower left, you can see the corrugated duct and the epoxy coated reinforcing going up the V-pier leg. And then in the right, again, you see these 2.5-inch diameter galvanized anchor rods, and you actually see the post-tensioning anchorage. Just another good view of how the steel arch transitions into the concrete V-pier. Again, these concrete V-piers all be painted white. Very large pours, 950 cubic yards per leg. John Gadja with MJ2 did the thermal control plan, the mass pour concrete plan. For the V-piers, we did use cooling legs to control our mass concrete. We had a 160-degree max, pretty typical, the 160-degree max with the 35-degree differential. And then the V-piers themselves were supported by waterline footings, 180 feet long by 48 foot wide, 9 foot deep, typically, except for that knuckle area, quite a bit deeper. And they're supported by 36 steel piles that are concrete filled down to mud line. And we reinforced concrete fill because we had the reinforcement come up into the footing to create a fixed moment connection. Again, remember, these are not thrust arches, although I guess at the abutment we do have a thrust force going into the abutment, but these are springing arches coming off these footings, so we needed that fixed moment connection. So we look at the piles themselves. These are steel pipe piles, 1 inch 1 inch thickness. 1/4 inch of that 1 inch is sacrificial, along with 2 coats of coal tar epoxy on the outside. Contractor did use spiral welded. Nominal driving resistance, 1,700 tons at the abutments, 2,000 tons at the V piers, right around 100 foot long. And we did use stat dynamic testing as well as PDA testing. We used a 2 stat dynamic tests to verify the capacity of the piles, and they proved to be very effective and efficient in doing that. So the way the contractor constructed the waterline footings and drove the piles, they used a precast soffit. You can see in the left, the concrete soffit is about a 1 foot 6 inch soffit, and they built that on the land, and then they fixed the forms, the wall forms for the footing, and then lowered this system by hydraulically into place, and then used that soffit as a driving template and drove the steel pile. Once the steel pile were in place, then they dewatered and placed the reinforcing steel. You can see on the right the reinforcing steel being placed. You can see the galvanized rigid steel for the post tensioning. And then these were very large pours as well, 1,700 cubic yard placement. Took 17 hours to place. And this was a 70% slag mix. And so we were able to not use cooling tubes for these because of the slag mix and the way this concrete was poured. And then lastly, I want to talk about the corrosion protection plan. The performance specifications, a couple things it required. You can see the table on the right literally came out of the performance specifications. So the foundations, piers, abutments, deck, and superstructure for the bridge have to last 100 years. And we were required to use the European code, the FIB model code for concrete structures. Those of you familiar with it, we used a probabilistic model with a target confidence of 90% to achieve the service life. And then we looked at basically two acceptance criteria. One was a deemed to satisfy for the freeze-thaw deterioration. And then we looked at the avoidance of deterioration for sulfate attack, alkali aggregate reactions, and the delayed intringent formation. We did, it was a performance-based and compliance testing to establish chloride mitigation coefficient and NT-build testing. And we looked at quite a number of mixed designs, both fly ash cement blends and slag cement blends. We looked at different mixes, different concrete covers, and looked at the developing this rapid chloride mitigation coefficient. You can see the table on the right, what we did for each of the components, the footings, the arch base, the precast deck panels, the concrete covers required, the cement mix, whether it was a fly ash or a slag, whether it needed inhibitor or not, and then the NT-build testing that went along with that. A couple of things that we had to do that were not addressed in the European code is how do we consider this PPC overlay? Again, the PPC overlay in and of itself it's less than 100 coulombs. So, and then the concrete itself had to be less than 1,150 coulombs. So basically, we said we've had 2.5 inches of cover requirement on the precast concrete deck panels. But then we said the PPC overlay essentially constitutes an additional 2.5 inches. So as we looked at the model, we basically used a 4.5 inch concrete cover. And then the European code also does not address the use of epoxy coated reinforcing. So we fell back to the Life 365 recommendations, which basically says you can consider an extra 14 years of service life for epoxy coated rebar. So we employed both of those to determine along with our mixes, the 100-year service life. And then the application and the actual testing in the field for the contractor has to do is basically that for one set of 4 cylinders every 100 cubic yards, they do what you're more familiar with in the permeability testing in the ASTM C1202, and again has to be less than 1,150 coulombs. So this is our construction project progress as of January 2021, excuse me. And basically, again, we're building, from that center arch in the river out towards the abutments, the east and west the abutments. And we expect to have this bridge open to traffic September, October of this year, with final completion of the entire bridge in May, or entire project in May of 2022. This is our website, so I would encourage you to go onto the website. You can see all of the various players that are part of the project, but also give you some more project details. So with that, I will turn it over and go to question and answer.
Thank you, Ken. We've got a few minutes here. We have caught up for the most part. So is there anything you would like to add? I know you did address one of the questions on the chat.
No, I did. I did answer the one question. So unless anybody else has any questions for me, I'm ready to turn it over to the next speaker. I will tell you, it's been an exciting project. You want an antidote, I guess, to fill a little bit of time. For me, for the most part, we as bridge engineers, it's a form follows function typically, meaning that we develop and design our crossings, strictly based on the needs for the mobility. And for this one, it's obviously very architectural driven, and it was fun to work with the bridge architect and the contractor and the design team in this regard, because we all had to be aligned and one-minded with one common goal and understanding that a signature structure was needed in this area, and it's been quite an interesting and rewarding process.
Ken, I do see someone just asked, what is the expected service life of the coal tar epoxy used for the steel piles?
Well, that's a good question. There's 2 coatings on it. That's something actually that we've been looking at, and it could be typically, right, it's like any other coating. 20 years probably is what you can expect. However, we have been in discussions with folks who are experts at coal tar epoxy. It's applied a lot, especially to drill rigs out in the ocean, marine applications. And what I've been told is if it is maintained every 3 to every 6 years, depending on the environment, that the coatings can last for a lot longer than that 20 years, meaning that if you spot repair as needed as the years go along, that it will last a lot longer. So, but it is a coating like any other coating. So it may or may not have to be maintained depending on how aggressive the river becomes over the years.
Okay, thank you, Ken. That was very informative and excellent presentation. We appreciate you being with us today.
All right, enjoy the rest of the conference. Thank you.
Thank you. All right, we are now ready to have our last session of the day. The title is The Effects of Market Concentration and Competition in the Paving Sector. The 2 speakers are Jeremy Gregory, PhD with MIT and the Concrete Sustainability Hub, as well as Jim Gillespie with the Virginia Transportation Research Council. Jeremy is a research scientist in the Department of Civil and Environmental Engineering and the executive director of the Concrete Sustainability Hub at the Massachusetts Institute of Technology. He studies the economic and environmental implications of engineering and system design decisions, particularly in the area of materials production and recovery systems. He received his PhD in MS from MIT and BS from Montana State University Bozeman, all in mechanical engineering. Jim is a senior research scientist at the Virginia Transportation Research Council. He has done transportation research for over 25 years on topics ranging from finance, forecasting, demand modeling, and cost benefit analysis to life cycle cost analysis, equipment management, and innovative contracting.
Hello, my name is Jeremy Gregory, and I'm a research scientist at MIT and the executive director of the Concrete Sustainability Hub. And I'm delighted to be with you today to talk to you about our research looking at the effects of market concentration and competition in the paving sector that I did with several of my colleagues that you can see here. And, a big motivation for this research for us is the fact that infrastructure spending is at such an all-time low. And you can see this from data that was published in the New York Times a few years ago. And this chart here is showing infrastructure spending as a percentage of GDP. And you can see that even though it was a few years ago, it's definitely at an all-time low. And so as a consequence, transportation agencies are being forced to do more with less. And one of the ideas that was proposed to us about how we might do more with less is to increase competition among product substitutes, because that could lead to lower prices. And before I get into that a little bit, what that means for the paving sector, I just want to make sure we're clear on definitions here, because for us, a substitute is a product or service that satisfies the needs of a consumer that another product or service fulfills. So in this example right here, we have a plastic or PET bottle and an aluminum can, but they both are holding Coca-Cola. So the material substitutes here are the PET and the aluminum. Now, if prices increase on the PET, we would expect then that fewer bottles of Coca-Cola would be produced using the PET, and instead there would be an increase in the use of aluminum cans. So there's a price elasticity that's occurring here in between the two different alternatives. Now, when it comes to paving, our question was whether or not the presence of competition between material substitutes would impact pavement material prices. And the terminology that I'm going to be using here is intra-industry competition. That is between firms that pave with the same material. So for example, if a job goes out and it's already been decided that it's concrete, this would be about competition among all the firms that are bidding to pave with concrete. And contrast that with inter-industry competition, and this is between firms that pave with material substitutes. So this would be bidders on a job that could go either concrete or asphalt, and that's the inter-industry competition. Now, the approach that we used to do this was a statistical analysis of the Oman bid tabs database, which you may have heard. It's a database that contains a whole bunch of data on projects that have been bid and also constructed as well, mostly by DOTs. And so the data that we used was from 2005 to 2015 across 47 states that provide that data. And what we did is we filtered it down to data that we felt like was really relevant to this pavement discussion. And so only things related to mainline paving. So we took out curbs and gutters. We also took out jobs that were really small, like maybe patching or just really short sections. So we felt like this was representative of what we consider to be paving prices. Then what we did is once we had all the prices in there, we then looked at a whole bunch of data for different sort of characteristics of those projects. So for example, we looked at what's the project size, meaning like what's the quantity of paving materials that are used, what's the overall market size in the state, and our metric for that is annual spending. Are price adjustment clauses used, which is really relevant to asphalt only. What's the number of bidders on a project? And that was our metric of intra-industry competition. And then lastly, what's the dominant market share? And our metric for this was the percentage of spending on asphalt concrete. And this was our metric for inter-industry competition. So the idea was that we would look at the statistical relationship between all of these parameters here, and then both asphalt and concrete paving prices, and see if we see any type of correlation that's statistically significant between these parameters and the asphalt and concrete prices. And just so you see, this is our metric here for the inter-industry competition, and this is showing the asphalt spending ratio across all states, with the lowest being, the lightest colors being in 55% and the darkest being in closer to 100%. And just for context, in Virginia here, over that time period, it was 99% spending on asphalt. Now, what we did then is we took all that data, did our statistical analyses, and I won't go into it. I can provide, a paper that gets into those details if you're interested. But what we found was a statistical relationship between both the asphalt prices and concrete prices and these different parameters. And how I'm showing that here is basically through the size of these boxes. This is called a box and whiskers plot. So the whiskers are really kind of extremes, whereas the box part is sort of mostly where the statistical significance lies. And what this means is that for, kind of the line down the middle is sort of the average unit price across all this different data, and the range means if we make any change to this parameter, how much of a change does it have on those unit prices? So what you see is that for both asphalt and concrete, just about the biggest factor is what's the size of the project. And that makes sense. Obviously, for more material that we use, that's going to lower unit prices for both of them. Whereas we see smaller effects in market size and the intra-industry competition. But the next biggest factor, certainly for asphalt and concrete, it's even a little bit bigger, is this effect of the dominant market share, which is that metric for inter-industry competition. So once again, we see that the statistical model shows there is a large impact of inter-industry competition on unit prices. What we could then do, we were then curious, well, like how much can we sort of take that information and translate it into a model where we can then try and estimate how much of an impact is that going to have on, would it likely have on paving prices. And so what we did is we then took that data and then created an estimate where we could say, like we have here, for a state spending an average of 5% on concrete, an increase to some other level of concrete market share would then have decreased paving costs by this amount. So like, for example, if we started with this 5% and then increased concrete spending to 10%, our model estimates that asphalt prices would decrease by 3% and concrete by 13%. And you can see that continues all the way up here. Clearly, there's a larger impact we see on the concrete prices than the asphalt prices. So once again, this is just this is looking at all the data across all the states, and is a way for us to try and understand what could be the impact of changing prices using this statistical model. The other thing that we can do is try and estimate what's the impact of competition on the amount of paving that you could do. This is literally our way of looking at, trying to do more with less. So once again, using that statistical model, then and making an assumption about a state with $100 million budget, and then some kind of average prices here for asphalt and concrete. If we increase paving on concrete from 5%, going higher, what happens is that you're able to pave more over as you increase that because the prices are lower. So even though your budget is fixed, you can do more. And so you can see as you get up to 25%, you're able to do 6.5% increase in that paving tonnage. So once again, this is just a way to kind of approximate what might be some of the impacts associated with competition based on the statistical model that we are able to create. The other thing to keep in mind is that what we have here is a correlation between these parameters and prices. So we can feel pretty confident saying that based on the historical data that we have, that correlation exists. But the thing we need to do, the next step, is to try to understand correlation versus causation. So we see that correlation, but we want to try and better understand what might be causing it and what factors would you change in order to see whether that's really true. And we see this happen a lot in medical studies. There's a lot of statistical analyses, that show a correlation between smoking and lung cancer, or exercise and mental health, or a healthy diet and life expectancy. So the statistical models show that, but the next step in all those studies is to do some more science to try to understand what could be that causation, and then that can lead to other guidance on prevention or other kind of objectives. So I think we have a similar opportunity there when it comes to competition. We see this correlation. What are some of the best mechanisms to implement that and actually act? And that's where we see a lot of opportunities going forward. So with that, I will finish up and be glad to share with you our website here and our email address in case you have additional information. Feel free to contact us if you do have questions, and otherwise I'd also be glad to answer any questions right now.
Good afternoon. Thank you for welcoming Dr. Gregory and me to your secret virtual clubhouse. Let me start by emphasizing that I am here neither to reject nor to endorse the findings and conclusions of this paper. I will make a few comments on the data and the methodology and the findings, and I will suggest some directions for future research that a highway agency decision maker might like to see. The heart of the paper is a regression of the prices of asphalt and concrete on a handful of explanatory variables. I infer that the regression estimates that our friends in the concrete industry find most intriguing are the slope coefficients that show how strongly the dependent variables, the unit prices, seem to respond to changes in the market share variable, which the paper tentatively takes to be a measure of inter-industry competition. The graph at right sketches these findings in qualitative terms. If you imagine a scatter plot of price versus market share for each of the contracts in the data set, the point at upper right where all the lines cross would be the middle of the cloud of points, where asphalt price and concrete price and asphalt market share have their average values. You can see that the unit price of concrete seems to respond positively to an increase in asphalt's share of the state pavement budget. You can see that the unit price of asphalt also seems to respond positively to an increase in asphalt's share of the state pavement budget. The paper's results and conclusions conjecture that we are seeing two opposing mechanisms at work here, one dominating in asphalt, one dominating in concrete. And we can talk more about these mechanisms in the questions and answers if you're interested. If we accept these findings as a cause and effect relationship, they seem to be telling us that a highway agency might get more bang per buck by reducing asphalt's share of the budget, provided that the life cycle cost difference between concrete and asphalt is not too big. Our friends in the industry already have shown their interest in this finding. Leif Watney of ACPA and Jim Mack of CMEX submitted a paper to DRB last August that refers to this paper we're discussing. They described very clearly the level of programmatic commitment to concrete that they would recommend a state DOT to undertake in order to exploit this apparent relationship between price and market share. Okay, as a state DOT employee, what questions do I have? My first question would be, could I see more tables and graphs describing the data set, especially the price variables? I understand that the authors are working to publish this paper. The authors very likely had to edit text and tables ruthlessly, maybe even tearfully, in order to stay within the journal's word count limit. I also understand that Oman invested time and effort to compile the BidTabs database, and they're probably not giving it away. Perhaps, however, the authors could make an expanded version of the paper available that includes a little more information about the data. I'll give two examples. Table 2 in the paper shows summary statistics for most of the explanatory variables, but not for the dependent variables, the prices of concrete and asphalt. Why are the summary statistics for the prices not in Table 2? Second, I like to joke that new statistics students imagine that regression will reveal a pattern in the data that they couldn't see with their naked eye, while old statistics students know that regression much more often reveals that the pattern they thought they saw with their naked eye could just as likely be white noise. So what's my point? Show us a scatter plot. Can we see the slope of the regression line in the scatter plot? Give me as many ways as possible to see the patterns in the data. My second question would be, could you tinker with the specification, that is, the regression equation? To be clear, I consider the comments from this point on to be directions for future research. The investigators already did a lot of conscientious work. I'm not suggesting they need to put more into this paper. The investigators have made a great many analytical choices that are as good or better than anything that I could or would have done. The treatment of the number of bids is one example. The functional form 1 over the number of bids has a simple, solid theoretical basis. Any functional form that had a more sophisticated theoretical basis would be a lot more complicated. This is just great. Now, why not use the same functional form for the contract quantity variable Q? This is to reflect economies of scale. If the vendor's economies of scale can be traced to fixed costs, then the reciprocal 1 over Q seems a more natural mathematical form than logarithm of Q. The variable the paper calls market size is really lane miles in the state system. I have two things to say about this variable. First, it appears to be another sort of scale factor. It's to reflect that a 1% change in asphalt's share of the pavement budget means more in a big system that buys a lot than in a small system that buys a little. This being the case, to introduce the effect of market size in an interaction term, market size S times market share DMS, may be a more natural specification than market size as a standalone variable. Second, this variable is probably more strongly correlated with geographical area than any of the other explanatory variables. It may very well end up capturing the effects that have to do with geographical area as well as the effects that have to do with the quantity of pavement purchases. Therefore, the meaning of the coefficient on this variable is going to be hard to interpret. The market share variable, the portion of the pavement budget devoted to asphalt, raises two big questions. First, market share is a narrow measure of inter-industry competition. The investigators freely admit this. They were constrained by data availability, as empirical researchers often are, and they used this because it was obtainable, and it is better than nothing. All the same, I think my colleagues in the materials division would protest that VDOT's programming and design processes do include a stage where asphalt and concrete are in some degree of competition with one another. The market share variable in this model just fails to capture that stage of the decision-making process. Therefore, the meaning of the coefficient on this variable is also going to be hard to interpret. If you challenged me to say what I would use as a better measure or as an additional measure of inter-industry competition, I wouldn't have a simple answer. Instead, I would move to my next comment. Would it be possible to estimate a demand function too? The second big question that the market share variable raises concerns the assumed behavior of the buyers, the state DOTs. Because the regression equations that the investigators estimate represent only the supply side of the pavement market, it's easy to assume implicitly that the share of asphalt in the pavement budget is just an arbitrary choice that each state DOT has made. That certainly is an oversimplification of what's happening in pavement procurement. I think we all recognize that for a variety of reasons, topography, soil, climate, traffic volume, even if the prices of asphalt and concrete were identical everywhere, some jurisdictions would use more concrete pavement than others. You can't look at this data set and not wonder if it can tell us anything about what influences a state DOT's choice between asphalt and concrete pavement. It is appealing, I'd say almost irresistible, to consider dealing with this issue head-on by estimating a system of 3 equations. One equation to describe the behavior of the asphalt contractors, one to describe the behavior of the concrete contractors, and one to describe the behavior of the state highway agencies. My last pair of questions would be requests for more data and more results. It would be valuable to see whether the analysis of an expanded data set, still based on the OM bid tabs, corroborates the pattern reported in this paper. Additional variables, such as those I mentioned earlier, topography, soil, climate, traffic volume, might reduce the noise in the regressions, and they might be needed for identification of a 3-equation system that included a demand equation. It would also be valuable to see whether the analysis of a different data set corroborates the pattern reported in this paper. By way of example, I'm told that West Virginia DOT has committed to buy more concrete pavement in the hope of getting more bang for their buck. Perhaps at some point we can look for data describing the outcomes in West Virginia. That's all. Thank you.
Thank you very much, Jeremy and Jim, for 2 very great presentations. We have officially caught up and have a little time remaining at the end of the day. So if you 2 would like to come online, feel free to add any kind of closing thoughts before we finish up for today.
Yeah, sure. This is Jeremy, and I just appreciate the opportunity for Jim to provide some comments on what we've done. And as he said, there are a lot of opportunities to take this in different directions. In particular, if there is more data we're willing that we have access to. And I think that, just like I mentioned at the end of mine, this is sort of a preliminary statistical analysis. And just like when we sort of do statistical analyses on health-related topics, we then want to understand the mechanism a bit more, and it would be a neat opportunity to be able to study this further, to see whether when we dive into what some of those mechanisms are, whether they really do still hold up to demonstrate some of these potential impacts of competition.
I watched the chat. I didn't. I'm thinking it's in the afternoon, and what would I want at this point in the afternoon if I were listening to all this? So I'm not surprised I couldn't see anything in the chat. But while I was trying to access the ability to type in it, I accidentally shut down my connection to Zoom. So I hope you guys can hear me. Good. I thank Dr. Gregory for his presentation, and I thank you all for listening. And I can make a few sort of appendix comments if anybody's interested and time permits, or if everybody just wants to, get some coffee and that's okay too.
I don't see any questions in the chat, so I think go ahead and make a few comments. It's okay.
All right. Well, and one question I thought might come up is when I was talking about the interpretation of your results, Jeremy, is that somebody might ask, well, all right, you say this means a DOT can save money by switching more of its program to concrete, provided the cost difference isn't too big. I thought somebody might ask what too big meant, and that calculation actually turned out to be a little trickier than you might suppose. But after some back and forth between you and Omar Sway, I think tentatively I have an answer that it's 50 to 80% bigger. That's if you interpret the findings in the paper as a cause and effect relationship, which you did emphasize. But that's the answer to that. That's what the paper is saying if you interpret this as a cause and effect relationship.
And is that 50 to 80%? You're saying, as we pointed out in some of our back and forth, typically we see asphalt prices reported in per ton and then concrete in per cubic yard. So
right. Yeah. With those units, if you measure, if you take the ratio of, well, wait, no, I'm sorry. I normalized them both to 1 at the average price in that little chart I put in my slide. And if you take those averages, I think it was about $70.50 per ton for asphalt and about $173 per cubic yard for concrete. Then what the paper implies is that when those are translated into life cycle costs per lane mile for 2 comparable stretches of road, and that involves making technical assumptions that are beyond my competence, then the life cycle cost of concrete could be 50 to 80% bigger, and you'd still generate net savings. It's a big number. And as you said, it depends on the interpretation. And that was the rest of my response presentation, is talking about some of the questions that I'd want to see answered before I was ready to run with that.
Okay. Thank you, Jim. And thank you again, Jeremy. Very good insight here as we finish out your presentations for the day. So thank you again for being presenters, and we really appreciate all the time and effort you put into your presentations and also being available to join us today. Thank you.
My pleasure.
All right. We are magically right on time as we have indicated in our schedule. And as we had indicated before, at this point, before we close, we are going to have a door prize drawing. For those that's been at our conference, we have a very high-tech, sophisticated way of pulling name tags out of a bowl. Obviously, we can't do that today. So basically, we are pulling up our registration list. And I'm going to use a little random number generator here and push. And it looks like the lucky winner today is Jewel Stone of the Georgia Department of Transportation. Congratulations, Jewel. We will be in contact with you to get a mailing address to get that gift card to you. Thank you all for joining us today. And please come back for day 2 tomorrow morning at 9 o'clock sharp. And day 1 is now officially adjourned. Thank you again.